So for today, we're going to focus a little bit on how to represent double replacement reactions that occurs and also not occurs at the same time using our models. So the first one on page 15 is a reaction that actually occurs. So if I were to write the equation, I have an example of aluminum chloride aqueous with potassium hydroxide, which is also aqueous, and together they are forming aluminum hydroxide. We need 3 of those because aluminum is plus 3 and OH is minus 1. And from my solubility chart, I know that this aluminum hydroxide is a solid. If you don't know how to figure out if one compound or one of the products is a solid or not, make sure to ask your neighbors, check how you could figure that out for a compound. Okay, so if we were to balance this equation, we would have to put a 3 in front over here and a 3 over here, and that should balance our equation. Okay, so if we choose this first beaker as our first compound, we have aqueous aluminum chloride. That means in an aqueous solution, everything are in their ionic form, so ions. They are separated like aluminum 3 plus, and for that we also have chlorine 1 minus, chlorine minus, chlorine 1 minus. Notice the amount that I put on because in this compound I have 1 aluminum with 3 chlorine counterparts. So that's why I drew 1 aluminum with 3 chlorine ions. Okay, so then the second compound is KOH, and we have the ratio of 1:1. Right, we have a potassium cation and a hydroxide anion. So if I want to draw 3 of those, because of that 3 coefficient in front, I would do so like this. And they're all mixed within that solution. Okay, so if these 2 are mixed in the beaker, we have, in the products, we have 1 solid and 1 aqueous. Okay, so I know that the solid is going to sink to the bottom, right? So I'm going to draw my aluminum hydroxide down here. This is all solids, right? And I also have 3 KCl aqueous solutions. So let's draw some K's and some Cl's in here. It doesn't really matter where you put them. You can spread them apart, you can put them close next to each other, it doesn't matter. Okay, so this is for a double replacement reaction that actually occurs. We have a solid that is at the bottom and they're not in terms of ions. Right? Notice for all the aqueous solutions, we have them in ions. Okay, so ignore the bottom part. We will not be doing this for this page and next page. All you have to do is to draw the model. Okay, so let's look at a double replacement reaction that actually does not occur. Okay, so we will start with KCl aqueous and NaNO3. This is also going to be aqueous solution, right? And together they are forming KNO3 when I switch the 2 cations, and we also have NaCl. So this is the time where you go back to your solubility chart and you figure out for each of these compounds, are they solids or aqueous? Okay, so from that we will know that potassium nitrate is aqueous and sodium chloride is also aqueous. So given that both of these are aqueous with no solids as one of our products, we know this reaction does not occur in a double replacement reaction. So if we were to draw the first compound in my first beaker, I have some potassium cations and some chlorine anions. right? And for my second beaker, I also have an aqueous solution, which I have some sodium cations and some nitrate anions, okay? So together we form also a solution, okay? So every species in there is going to be in their ionic forms. So we have the K, potassium cation, nitrate anion, sodium cation, and the chlorine anion, right? We don't have a solid at the bottom. Everything is just floating around freely within the solution, okay? Also ignore the bottom part, and that's all I have for you today. Make sure you are doing many practices and staying warm.